In homework 7.3, we look at a complex Brayton cycle using the cold air standard method, but this time we're going to use a more complex system to model a gas turbine power plant. We're going to use something called compression with intercooling. So we'll have two stages of compression and we'll cool the air in between the two stages. And then we're going to have multiple stages of expansion in different turbines with reheat between them. We're also going to add a component called a regenerator, where we take some of the hot exhaust gas out of the last turbine and use to preheat the air going into the first combustor. So let's start with a little sketch of this. Just get my drawing tools. So we'll start with our first compressor, call it compressor 1, and then we'll cool it. Let's call this the heat exchanger. In this case, we have Q out. And it goes into a second stage of compression. Compressor 2. Now we could do several of these, have another heat exchanger or an intercooler, and then have another stage of compression. But we'll stop with that. We'll run it into something called the regenerator. And it will come out of the regenerator into another heat exchanger. This is where we burn our fuel and have significant Q in. Then we'll run that into our first turbine, have a reheat, which is also a heat exchanger. So we heat it again, and then into another turbine. Then we'll come out of this second turbine, and I guess I'll go on top here. Back into this regenerator. So we have internal heat transfer here. And then through another heat exchanger, where we have Q out, and finally back into compressor 1. So let's label these states, starting with the inlet to compressor 1 is state 1, state 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that was a little hard to see what I had there, so let me just label that. That's my regenerator. And I have some internal heat transfer going from this hot stream to the cooler stream. And I got in the way of my number 4 there. Okay, hopefully that's readable. Okay, turbine 2. So we're doing this cold air standard. So we're assuming whenever trying to find H, we can replace H just with CPT. So this is cold air standard approach. And when we have pressure rise or pressure drop in a component and it's isentropic, so if S equals a constant, then we're going to use relationship between temperature and pressure with this expression T2 over T1 equals P2 over P1 to the K minus 1 over K. So that is true for constant entropy, specific heats, constant, and an ideal gas. So with those assumptions, we can use that. And then we'll make note that shows up and given in different components. Let's draw a UV diagram. So we'll start with isentropic compression from state 1 to state 2. And then that heat exchanger, the temperature is going to drop, so it'll be cooling. And so we'll be going in this direction along a constant pressure line to state 3. And then we'll have more isentropic compression to state 4 in the second compressor. So that now we have the compressor, the cooling in the intercooler, and then from 3 to 4 compression in the second compressor to the highest pressure. Then there's some heating to state 5 in our heat exchanger. So that's constant pressure since it's an open system. And then we have another heat exchanger that continues to heat it at constant pressure to state 6. Then we go into a turbine, so the pressure will drop. Doesn't have to match this other pressure. Then we have some more heating. It's again constant pressure. This was a constant entropy process. And then in this next turbine, it has to drop all the way to pressure 1. So this will drop all the way down to pressure 1, constant entropy to state 9. Then it goes through the regenerator, loses some of its energy to state 10. And then finally, in the last heat exchanger, cools back down. These are both constant pressure processes. So that is our PV diagram for this more complex system. It looks a lot like the Brayton cycle, just with this little shift in the 2 entropy rise section and the entropy drop section in the turbines. Let's walk through a little bit how to calculate these things. I'm not going to go into as much detail as I did in Homework 7.1 video, because that one maybe was the first time you'd seen it. So determine the temperature at state 2. So we're going to use the relationship that T2 equals T1 times P2 over P1 to the K minus 1. And P2 over P1 is what we're calling RP1. So RP1 equals P2 over P1. RP2 would then equal P4 over P3. So those are given. So it would be RP1 in this case to the power K minus 1 over K. So that's how we'll find T2. Then determine the pressure at state 2. Well, that's what RP1 is. So P2 just equals, in other words, can we write this? P1 times RP1. So determine the temperature at state 4. Now, I should point out that both T1 and T3 are 300 degrees. So what happens is it comes in at atmospheric temperature into our first compressor, and then the heat exchanger cools it back down to atmospheric temperature. So we have just atmospheric air blowing across this heat exchanger, and it cools that hot air coming out of the compressor down. Of course, it's in a inside a pipe, so that there's no exchange of mass, but the cool outside air can cool it back down to close to atmospheric temperature. So we're going in T4. We use the same expression we did for T2, except we'll change it to T4 divided by T3 equals the pressure ratio. This time it's a different pressure ratio. So T3, which is given, same as T1, T3 equals T1 to this time times RP2 to the K minus 1 over K. So that is going to give us T4. And then the pressure for P4 equals P3 times RP2. And then we have to note again that P3 equals P2. The temperature at state 5, we're going to have to use, we'll have to calculate this later, but let's take a look at the regenerator. So our regenerator has, let's just redraw this. So it has this flow in going this direction. where this comes in at H9, it exits at H10. And we have a flow going in this direction, so it's a counterflow heat exchanger. Comes in at H4 and exits at H5. And so we want to have our system boundary here. And we'll note that the hottest thing in this flow is state 9. So it's coming out of the last stage of the turbine. So turbine 2 comes out still fairly hot, comes into this heat exchanger. It will be hotter than T5, or than T4, so it can heat that up. So the maximum enthalpy, so H5 max would be H9, because T5 max would equal T9. So the hottest temperature we can get state 5 to is to temperature 9. And since enthalpy is just a function of temperature, then H5 is dependent on the maximum value it could get to is H9. So if we want to set up an efficiency, we'll call it the regenerator effectiveness. So I'll just put an efficiency symbol, eta, and then R for the regenerator equals, we'll say it's the actual enthalpy change. So over delta H max. And so the actual would be H5 minus H4. And the maximum is H5 max, which is H9 minus H4. So if it was a perfect heat exchanger, in other words, it was infinitely long, or we had infinite time, and very, very slow flow rates and no heat loss, then we could transfer all the energy. If it was less than that, if it came out at a lower enthalpy than that, then we'd have some efficiency less than 1. So finally we get that H5 equals H4 plus the regenerator effectiveness times H9 minus H4. Now, since this is a cold air standard problem, we can determine that all these H's could be replaced with CPT, and the CP is the same. It's not dependent on temperature, so we can divide the whole equation by CP, and I would get, so this is for cold air standard only. This other expression is good for the air standard problem, which would be T5 equals T4 plus regenerator effectiveness times T9 minus T4. And we're using that relationship that we can replace the enthalpies with CPT. So we can write an expression here for temperature 5, but what we realize is we'll need T9 before we can actually get a number for it. So it equals T4 plus the regenerator effectiveness, which is listed here as 90%, times T9 minus T4. So at this point, we don't have temperature 9 yet, so we have to wait and come back to that answer. Okay, then the temperature at state 7, we're told the temperature at state 6, so we can find out based on an isotropic relationship what the temperature at state 7 is. So we can write that as T7 over T6 equals P7 over P6 to the K minus 1 over K. And the reason we can do that, that's an isotropic process from 6 to 7. And we are given, should be given, in this case, we're not given a ratio, we're given pressure 7. So we just express that as P7 over P6. So I don't have the numbers, but P7 is given as 546 kPa. And then where I calculated P4, so P6 is equal to P5, which is equal to P4, since those are all isobaric processes. So technically we could divide by P4, which we've calculated here. So, but I'll go ahead and just still write it as P6 to the K minus 1 over K. So if you've been calculating the numbers, you could put that number in here. Now I have pressure 7 is given. So pressure 8 equals pressure 7. And we can just put that equation in here. So that's going to equal T7 equals T6 times P7 over P6 to K minus 1 over K, noting that we do have an equation for P6. So now state 9, we can find from state 8 in the same way. So we use the same equation. So T9 over T8 equals P9 P8 to the K minus 1 over K. And here, pressure 8 is the same as pressure 7. So we found that's to be 46. So P9 or P8 rather equals P7. And we also note that P9 equals P1, since our last two processes are isobaric. So we had pressure 7 already, it was given. That's the same as pressure 8. And pressure 9 is not given, but we note that pressure 1, pressure 10, and pressure 9 are all the same. So those three are the same. So we put those two known values in now, and we can calculate the value for T9. So let me just put C below. And T9 equals P8 times P9 over P8. Again, those values are known now. K minus 1 over K. And so now we can put that T9 into this expression here, and we can go back and get a value for T5. Now to find the net work through the power plant, it will be all the compressor work plus all the turbine work, depending on the sign we use. If we make our compressors calculate as negative values, then we add them. If we make them as positive values, we subtract the compressor work. So the net work. And if we do it, I think per unit mass, because we're not told the mass flow rate in this case. So this would be everything divided by m dot, but every component has the same mass flow rate going through it. With one exception, the regenerator, it has m dot going that way and the same m dot coming back the other direction. So we can write this as equals, if we want to do inlet minus exit for everything, then we'll add them all up. So H1 minus H2, that would be compressor 1 plus H3 minus H4, that would be compressor 2. So compressor 2, compressor 1, plus the work for turbine 2. Of course, all these are per unit mass. And then plus the work for, let's do turbine 1 first. So that would be plus 6 to 7. H minus H9. So that's our work per unit mass. And then calculate the external heat addition per unit mass. So we have two places for external heat addition, the Qn from 5 to 6 and the Qn from 7 to 8. So that would be Qn per m dot would equal H6 minus H5 plus, so this is heat exchanger let's just say Qn 5, 6, since we have a lot of things called heat exchangers, plus Qn 7, 8. And then our total efficiency for this complex system would be the net work per unit mass divided by Qn per unit mass. And this is cold air standard.